Good day everyone, we are the group 6 and for today we will tackle about the expanding universe and here's the content and for the learning goals. By the conclusion of this chapter, you should be able to apply those learning goals at the end of the module.
Good day everyone, my name is Artisha El Caballero. So for today, I'm gonna discuss to you the expanding of 20th century astronomers discovered the universe and galaxies. The nebula are found in interstellar space, which is the space between the stars. The Helix Nebula is the nearest known nebula to the Earth. It's the last remains of a dying stars, perhaps the sun because of their nebulous nature. These objects were originally termed nebula. Only roughly 100 of this smudge of light had been discovered with and without telescope, prior to the 1780s. Charles Missy in 1730 and 1817, an astronomer compiled a category of 103 nebulous objects. In 1784, and astronomers begin to notice systematic change in the appearance of nebula around this period. The original three nebula classifications categories are diffuse, elliptical, and spiral, were based on these characteristics. What chemical elements form in the early universe? The Milky Way is just one of many island universe that had been dubbed galaxies. Gala, which means milky in the Greek. The most pervasive nebula are gas and dust clouds. Near Earth in the Milky Way galaxy is a collection of a dust, gas, and millions to hundreds of billions of stars, held together by a gravity. There are billions of galaxies in the universe for more than there are stars in the Milky Way galaxy. The majority of the galaxies are so far that they appear too small and faint to be seen with anything except the highest powerful telescope. Because of the Milky Way was large enough to embrace everything in the universe. He assumes spiral and elliptical nebula were contained within it. Herbert de Cortes, year 1872 and 1942, of the Lick Observatory in California, supported the earlier, smaller model of the Milky Way. While the Great Debate did not resolve the matter of time, it did not set the stage and lead the way for Edwin P. Hubble's. In 1889 and 1953, later work which dramatically revolutionized our understanding of the universe. Hubble discovered some variable stars in the spiral nebula. Andromeda, using the freshly completed 100 each telescope on Mountain Wilson. High above, then little city of Los Angeles. He noticed that the stars were similar to, but fainter than the Cepheid variable stars discovered by Henrietta Leavitt in the Milky Way galaxy. And the Nervi Magellanic Cloud Nebula, making use of Cepheid variable period luminosity relationship, Hubble's converted his views of the stars into the distance values for these objects. Scientists cannot go from the Milky Way to a galaxy in the far reaches of the universe to compare conditions. They may, however, compare light from closer and far away regions in a distant universe to see how features appear to let the same or different.
The cosmological principle. So what is cosmology? Cosmology is the study of space, time and the dynamics of the universe as a whole. So Alexander Friedman produced a mathematical models of the universe. In his model, it assumes that the Earth is not in a special place in the universe, and that on large scales, the physical properties of the universe were the same everywhere and in every direction. Cosmological principle states that the physical laws apply everywhere. We have used this principle when applying laws of physics and chemistry to objects near and far in the universe. The cosmological principle is a testable scientific theory. An important prediction of the principle is that the conclusions that scientists reach about the universe should be more or less the same regardless of whether they are in the Milky Way or in a galaxy billions of parsecs away. Homogeneous and isotropic aspects of cosmology. Homogeneous and isotropic aspects of cosmology principle. Homogeneous are all places look alike but no special location, while in isotropic are all directions look alike but no special direction. Did you get it? It says that all places are the same, but it but it's not a special location, and that is homogeneous. While in isotropic, all directions are the same, but it's not a special direction. The distribution of galaxies is isotropic and homogeneous. As you can see in the picture, there are four pictures. So the homogeneity and isotropy in four different theoretical models of a universe. Blue arrows indicate the direction of view. So in letter A, the distribution of galaxy is uniform. So this universe is both homogeneous and isotropic. While the letter B, the density of galaxy is decreasing in one direction. So this universe is neither homogeneous or isotropic. In letter C, the bands of galaxies lie along a unique axis, making this universe anisotropic. And the last picture, which is the letter D, the distribution of galaxies is uniform, but galaxies move along only one direction. So this universe also is not isotropic.
Hello and good day everyone, my name is Nasano Basanyas and I am assigned to report the universe is expanding. Now, the universe is expanding, but how does it expand into? Well, in 1929, Edwin Hubble's astronomy observations gave us a definitive answer. His observation from the night sky found all faraway galaxies that move away from the Earth. It means that the further the galaxy, the faster it recedes. How? Well, consider a cookie when it puts in the oven. It rises and expands just like the dark chocolate on the top. In this, we can imagine that the stretching or expansion of intergalactic space will make the galaxies recede from each other. And then the astronomers were also trying to differentiate whether the universe is isotropic or homogeneous. In the cosmological principle, the mentioned homogeneous and isotropic have different meaning, and that homogeneous has the same composition and properties at all places, whilst the isotropic is that something is the same in all directions and it is easier to test directly than homogeneity. The next one is the Hubble's law, and it is considered the first observational basis for the expanding of the universe. It is the pieces of evidence that most cited to support the Big Bang model. The Hubble's law also tells us how fast the universe is expanding, which can be used to determine the age of the universe and its history. This Hubble's law is attributed to the Doppler effect. a change in wavelength that results when a given source of waves and an observer are in motion with respect to each other. Hubble's brilliant observation was that the redshift of galaxies was directly proportional to the distance of the galaxies from the Earth. And that leads to the statement of Hubble's law that says the Earth is located a uniformly expanding universe and that the expansion looks the same, regardless of the location of the observer. Now, we were going to find out how they know it expands. Well, the observation of the light, just like the Doppler effect, that the given source of waves like light, radio waves can be used to know the distance of the galaxies and the objects. For example, astronomers often use the term redshift to know how really far objects are because redshift indicates the galaxy's distance. To understand what really cosmic redshifts is, that we must think about sound. For example, a police car. You can hear the siren because the waves travel through the air into your ear. And if the police car is moving, the sound in front of it are compressed and creates a higher frequency sound. And the sound waves behind it are stretched out, creating a lower frequency sound. Like for example in the picture, the light is quite similar. It also travels in waves. The light waves are able to be compressed and stretched just like sound. Blue light has shows wavelengths than red. The blue shifted is shifted towards the shorter wavelength and the waves objects move away from us. The light waves are now stretched called red shifted that shift to a longer wavelength. How they find it? Well, the light from the most distant objects in our universe is redshifted, very redshifted. By using cosmic redshift, astronomers are able to measure the distance of galaxies as far as 12 billion light years away. Well, astronomers also observed that the objects with greater and greater redshifts they are seeing increasingly younger stages of the universe. And that's all my report. Thank you for listening.
Good day, everyone. I am Cleone Alinid, and I am here to continue the discussion. To start with, the universe began in the Big Bang. Hubble's law helps us to fully understand and distinguish the beginning size of our universe to be exact. To simplify, we know that the age of the universe is 13.7 billion years old. If we are to minus the half presence of its age, all of the galaxies in the universe is equivalent to the half of the distance of current locations of the galaxies. To sum up, the universe today must have been concentrated together at the same location. Expansion started with the Big Bang. Everything in the entire universe was condensed in an infinitesimally small singularity, a point of infinite denseness and heat. Suddenly an explosive expansion began. And now, have you ever wondered how astronomers determine the age of the universe? Knowingly, there is no such human who live exceedingly and have witnessed the birth of the universe. And let's go back to Hubble's law. It says there that the velocity of precession of a galaxy is proportional to its distance from the observer. So here's how the Hubble's law helps us to calculate the age of the universe using the formula below.
So this is the formula. Time is equals to distance over velocity is equals to distance over Hubble constant times distance. And these are the given equivalencies. Now, if we are to find the time and the given r, the distance with 30 megaparseconds, and recession velocity of 2,100 km per second. So what we have to do is to substitute the following given and follow the solution provided, and you will get the age of the universe.
And now, let's move forward. We have misconceptions that the galaxies are flying away, which in fact, that galaxies are not flying apart through space, but it expands like balloon, which illustrated here. Moreover, the Big Bang happened everywhere. It has no exact point or center, but everything is part of it. Now, the expansion is described with a scale factor. As we can see, there are grids inside the balloon, and dots along with it. The dots stands as the galaxies. As the balloon is inflating, the spaces between the dots expands, but the location stays the same, so that's how the Hubble's law defined the expansion of the universe.
Astronomers observe radiation left over from the Big Bang. Ever since the Big Bang around 14 billion years ago, our universe has been expanding. But how do the scientists know that the universe is getting bigger? It's due to a phenomenon known as a Doppler effect, in which the frequency of a wave changes based on how the object is moving, and it called it the redshift. And how do we know that the radiation of our universe is becoming cooler as it expands? Blank black body spectrum. As the universe expanded, this radiation would have been shifting to longer and longer wavelengths. Recall the Wien's law from the chapter 5, which states that the temperature associated with the Planck black body radiation is inversely proportional to the peak of wavelengths. Shifting the Planck radiation to longer and longer wavelength is therefore the equivalent of shifting the temperature of the radiation to lower and lower values. As illustrated in the 19.15, doubling the wavelength of the photons in a Planck spectrum by doubling the scale factor of the universe is equivalent to cutting the temperature of the Planck spectrum in half. In the late 1940s, cosmologists Ralph Alpher and Robert Harman and George Gamow conclude that this radiation should have been Planck body spectrum with a temperature about 5 to 50 Kelvin. Wien's law. Wien's law tells us where the star's brightness at its maximum. In other words, Wien's law tells what is the color of the brightest object. As the surface temperature rises, this peak, intensity or brightness shifts towards blue and of the spectrum. As the surface temperature decreases, the peak intensity or the brightness will move toward the reader end of the spectrum. Measuring the temperature of the CMB or a cosmic microwave background. The cosmic microwave background radiation or the CMB for short is the faint glow of light that fills the universe falling on Earth from every direction with nearly uniformly in the intensity. It is the residual heat of the creation of the afterglow of the Big Bang streaming through space. These 14 billion years, like the heat from the sun, warm rock, or radiated at night. The CMB measures Earth's motion relative to the universe itself. Unlocking the early universe to reveal those secrets, cosmologists study the patterns of the hot and cold spot, frozen into the CMB, and decompose those spots into their constituent size. While most of the hot and cold spots are about 1 degree in the sky, they are overlaid on the fluctuation with the larger sizes, the sizes of the breakdown of the CMB temperature spot, or the fluctuation. The rate of the fluctuation signal at different scale is associated with the universe age, its ingredient, its expansion rate, and the first star lit up the cosmic by accompanying computer models to the signal's rate. Researchers can piece together what the early universe looked like and how it evolved. That's because the CMB maps and their statistics lead to the called standard model cosmology. The recombination of the universe. Penzas and Wilson predicted a hot early universe arriving independently at the same basic conclusion as Alpha and Gamow. After the Big Bang, atoms could not exist As the universe expanded, its density and temperature dropped until ions and electrons could recombine to form atoms. This is known as the epoch of recombination.
Good day everyone. I am Christopher Camino and I'm going to discuss the origin of Big Bang nucleosynthesis. Big Bang nucleosynthesis is when the universe was only a few minutes old. Its temperature and density were high enough for nuclear reaction to take place. Collision between protons in the early universe built up low-mass nuclei including deuterium, a heavy hydrogen, and isotope of helium, lithium, beryllium, and boron. This is process called Big Bang nucleosynthesis. The second is the calculated prediction of abundances of deuterium, helium, and lithium. The first thing to note in figure 19.19 is that about 24% of mass of the normal matter formed in the early universe should have ended up in the form of very stable isotope for He. And regardless of total density of a matter in the universe, indeed 25% of a mass of normal matter in the universe today is in complete agreement with the prediction of a Big Bang nucleosynthesis. The third is the other isotope abundances formed in the Big Bang. Comparing current abundances with model of isotope formation in the Big Bang help pin down the density of an early universe. It's shown as a roughly horizontal pastel band in figure 19.19. Beginning with the abundances of isotopes such as 2He, deuterium, and 3He found in the universe today. The fourth is the major prediction of Big Bang theory are resoundingly confirmed. This is a price agreement that holds for a variety of isotopes. To reverse this, cosmologists can start by measuring the amount of normal matter in around galaxies, then comparing that to calculation of what the chemical composition of a Big Bang should have been. The findings are very consistent with the level of component found in nature. The fifth is the agreement also provide a powerful constraint on the nature of dark matter. So the dark matter cannot be made of ordinary matter made up of neutrons and protons. If if it were the density of neutrons and protons in the early universe would have been much higher, and the ensuing abundances abundances of light elements in the cosmos would have been very different from what we see now.